Alright, hi everyone. So in this video, we are going to discuss about topic 2 in Pure Maths 1, which is function. So the video will be divided into two parts. For the first part, we'll be discussing on the definition of function and some terminology, and then together with composite function and inverse function. So for the second part for the video, we'll be focusing on transformation in function. Okay, so a function is just a relation that connects one set to another set. So this set normally the input, okay, the set of input is called as domain. So normally we denote it as X. So the set of output is called as codomain, and normally we denote it as Y. Okay, so if let's say we have a simple function here, if f of x is equal to 2x, so which means if let's say I have 2 and I have 4 here, okay, let us use 5 instead. Okay, so 2 will be maps on 4, then after that 5 will be maps on 10. Okay, so I guess you shouldn't have any problem with this part. So some other term that you need to know is 4 is the image of 2. Okay, so the function helps us to map 2 on 4. So 4 is the image of 2. So on the other hand, we also say that 2 is the image of, 2 is the object of 4. Okay, so it's the same thing when we say 5 is the object of 10 and 10 is the image of 5. Okay, and the image set is normally called as range. Okay, it's the set of image that we have. So codomain is like any possible output. Range is like the output that does really happen. Okay, so for functions, function has to only produce one output for each input. So meaning that for the relation that we can accept, it will be one-to-one relation and also many-to-one relation. Okay, so one test that will be helpful to help us to identify whether the relationship is a function or not is by carry out a vertical line test. Okay, so I hope that you still remember. So if let's say I give you an example here, you have this is like a one-to-one graph, right? Meaning all the x will produce only one y. So a many-to-one relationship will look something like this. Yeah. So you can see that if I go from this way, then it creates. So for this point and this point, it's different input, but it come out with the same output. So that's why this is like a many-to-one. So vertical line test is as if you try to imagine that you have a vertical line, then you try to move around this graph, it will only intersect at one point. So that's why it's a function. So if let's say you have a graph that looks like this, so this is a one-to-many relation. So you can see that if I compare to this point and this point, so you see one input, I have two output. So that's why when you try to move around the vertical line here, you will see that it intersect more than one point. So that's why it didn't pass the vertical line test. So that's why one-to-many is not a function. Okay? Alright, so for the second thing, we are going to talk about composite function. So as we know that composite function is actually a combination of two or more function, right? So at your standard, normally it's like two functions, we combine them together. So if let's say I have a set of input here, which is x, so this is a function of f, okay, and this is the function of g. Alright, so what happened here is after I substitute x inside the function of f, then the image that I got out from this function will be called as fx, correct? So this is like my y equals to fx. So if let's say now I try to substitute my new object into the function of g, then what do I get? Then I will get g fx. Okay, so basically like fx now become my new object, then I'm going to substitute into a new function. So this is called as gfx. Okay, so you must remember that from x, for you to get to the last one is gfx. Okay, so it's like you substitute x into function of f, then after that you get a new image, then after that that one become your new object for your g, so that when you combine it's called as gfx. Okay, so now something that you might need to be careful is that I think you already know this, so just a revision. So gfx is not the same thing when we talk about fgx. Okay, so for this term, f happened first, then after that substitute into g. So for this term, it's like g happened first, then after that you substitute into f. So the answer will be different. Okay, so the other method for us to write, for example, if let's say you have ffx, okay, you can always write it in the term of f square x. All right. Okay, so something that you might be very cautious in composite function is that for example, we talk about this function. So gfx only exists if the range of f of x is within the domain of gx. Okay, so I'm going to explain this part for a bit. So this is very important for your paper. I mean, this is a very quite popular questions that they will ask this. So you must make sure that, okay, you see, if let's say my constraint for my domain that I can accept for fx, if let's say it's a positive number, so if let's say my x is a negative number, then fx is not valid, correct? So that's why it's the same thing if we want to create a composite function. So if let's say that now x is substitute into fx, so now you form a new object to gx already, correct? So that's why gx has its own domain. So you must make sure that the range that you get out from fx, it must be satisfy the domain for gx. So that, for example, if let's say gx only accept positive answer, so that's why you need to make sure that from the beginning of your substitution, your x should be a number that after you substitute into fx, you will get a positive value, then only you can substitute into gx. Okay, so that's the idea. So gfx only exists if the range of your gx is within the domain of your, the range of your fx is within the domain of your gx. Okay, so for the last one, we talk about inverse function. Okay, so I think this is easy. So inverse function is like a function that undo the do actions that it happened before. So for example, if let's say I have f, okay, so after it maps onto the other set of value, then I get f of x, correct? Okay, so meaning that now if I want to undo this process, then it will be called as inverse. Okay, so meaning that if let's say fx equals to y, okay, which another words, it means that for me to get back my x, then I need to do the inverse of y. Okay, so that's the idea. So the other thing that you can say is like inverse function undo the f function, correct? So that's why f negative 1 fx, okay, or we talk about f negative 1 x will brings you always back to x. Okay, so meaning it after you substitute into the function, you get your image, then you do put inside your inverse function again, then you are going to get back the exact same object. Okay, so you remember just now we said that for function, right, it only accept one-to-one and many-to-one. So you can try to imagine if let's say now you have an inverse function, is the constraint still be the same? Because now you see one-to-one, you do not have any problem here, right? Because if let's say you have one input to one output, then which means when you try to put it in inverse function, it also give you the exactly same thing. But when we are talking about many-to-one function, can you try to imagine if we try to put it and find out the inverse function, right? So what do you have? So from many input to one output, it will become one input to many output. So that's why for inverse function, we can only accept one-to-one relation. Okay, because for the constraint for function to be valid. So that's why the other test that we need to put in, so that we need to check that whether you have an inverse function or not, is except by doing vertical test, you also need to do horizontal test. Okay, it's like horizontal line test. So the explanation will be at the exactly same thing just now. So if you can recall previously when we try to learn this part, right, I explained that if let's say you have a function which is a many to one function, that you actually want to find out the inverse function, how can your function to be valid? It's by setting a correct range. It's by setting the correct domain. So that you will have, like, for example, many to one, so something like this. Okay, so if let's say, because when we try to do this, then you can see that this is a many to one function, right? So that meaning that we cannot have inverse, because when you try to imagine, if let's say I try to draw it in another way, so now when we talk about inverse function, then for one input, you will try to have two output already. So that's why in this case, how are we going to solve this? Is we are going to set a set of domain so that it will become a one-to-one function. So for example, instead of taking the whole graph here, then I'll be taking maybe the front part only. So now this graph become like a one-to-one function, or I take the second half so that it become a one-to-one function. Okay, so that's why in some questions that, for example, if let's say you have a square, then they want you to find out the inverse function, where normally you try to solve and you see you have positive and negative square root, right? So normally you need to refer to what is the range and the domain that given in the question, and you need to identify whether you should follow the positive sign or negative sign. Because when you are putting plus and minus, mean that you indicate that this is like a one-to-many function already, which is not correct in terms of function. So like function only can accept one-to-one or many-to-one, correct? So if let's say you are doing like this, meaning that from one input, you are going to get two output. So this is a one-to-many relation, which is not a function. Okay, so this is something that you should be mindful of. Then something important will be, yeah, the domain. So we talk about this as well. The domain for f of x, the domain for inverse will be equals to the range of the original function. Okay, so the same thing, meaning that the range for the inverse will be equal to the domain for your original function. Okay, which makes sense, right? For example, when you look at this, so this is the object and this is the image. So now when you try to do the inverse, then this become your object, then this become your image. So that's why the domain become the range. Okay, so that's the idea. So one last thing is that the graph of the graph, okay, of f of x and f of negative 1x is the reflection on the line y equals to x. Okay, so if you think that you have like, you feel like some idea here is like very blurred to you, then you might need to go back and refer on the certain part. So this is a thing that you should know when you try to solve the questions in function. Okay, so now let's try to look at the part where we discuss about transformation. Alright, so for the part for transformation, we'll be looking at it in like two big categories. So for the first one, we are talking about the vertical movement, and second part is like the horizontal one. So we are going to look at the difference and then how do we express it in function. Okay, so the first one, which we start from y equals to f of x plus a. Okay, so for this function is a translation in a y direction, which is like 0, a. Okay, so which means, for example, if let's say that we have this original graph, okay, so maybe when we try to move up, then this is going to be what happened lah. Okay, so you can see that the shape is like still the same, so it's just that now it's been translated upwards for like a units. Okay, so this is when a is positive. So if let's say you have translated downwards, then it will be a will be a negative. Okay, so for the second one, which is a translation as well, which is like, for example, y equals to f of x plus a. Okay, so in this case, it's a translation, but is a translation in the direction of x-axis. Okay, so the translation here will be negative a and 0. Okay, so this is something that different than the first one. So the first one, when we talk about positive, then it's the same thing where we have positive, then it move upwards, then after that negative move downwards. Okay, but for this one, when you plus, right, actually what happened is the translation is actually negative a, meaning that it will go to your left hand side. Okay, so if let's say now this is my original function, okay, so after I actually move it to left hand side, so this is where I have a is positive. Okay, so meaning that if let's say I have one more is at the right hand side, then it will be giving me a negative a. Okay, so meaning, for example, if I move for 5 units over here, then it will be fx x minus 5. So if like 5 units to left, then it will be x plus 5. Okay, so that's the idea. So the second one, we talk about reflection. So for a vertical one, then we have y equals to negative f of x. Okay, so for this part, which means we have reflection in x-axis. Okay, reflection in the line of x-axis, meaning that, for example, if let's say this is your original graph, okay, so after you put a negative for the graph, then it will become something like this. Okay, so it's reflection in x-axis. So for a horizontal movement, then it will be y equal to f negative x. Okay, so in this case, we are talking about reflection in y-axis. Okay, so meaning that it reflects from left to right, from right to left. So if let's say I have a graph that looks like this, yeah, perhaps I try to draw like this. Okay, which means after I reflect, then I'll get something that looks like this. Okay, so that's the idea. So this part reflect to left hand side, reflect to right hand side, reflect to left hand side. Okay, so this is for reflection. Okay, and for the last one, we have stretch. Okay, so let's start with the vertical one first. So you have the function like y equals to a f of x. Okay, so now this is the stretch with scale factor a, and the stretch is actually parallel to y-axis. Okay, so let me try to give you a simple example first. If let's say you have a graph that looks like this, okay, so this graph was intersecting at the point of 2. Okay, so if let's say now when you try to stretch it with a scale factor of 2, then what happened is you can try to imagine that if let's say y equals to x and y equals to 2x, so all your value that you got for your y will be like double up, correct? So now your intersection point is at 4 here. So this is like a stretch. For example, go to to fx. Okay, so meaning that if let's say I have a graph that is here, and this is like 1. So compared to my original graph, that meaning that this will be 1 over 2 f of x. Okay, so it's a stretch with a scale factor of 1 over 2. Alright, so that's the idea. So you can see that for the x-intercept, it doesn't change. So what happened is like just a stretch pulling upwards or like it's compressed downwards depending on your scale factor. So this is like parallel to y-axis. Okay, so let me try to give you like another example here. So this is like a very ideal case which is like easier for us to understand. So now if let's say you have a graph that looks like this. All right, let me try to draw it again. Okay, so you have a graph that looks like this. So how is that going to happen if let's say this is your original function and now you stretch it for 2 times? Okay, so you see definitely your intersection here will be like double up, correct? Okay, so if let's say this is like -2, then this is going to be -4. So your minimum point was originally here, then it will be going lower. So do you think that is there any change for the x-intercept? Yeah, there will not be any changes because you see if your y is 0, when you multiply with no matter what is the scale factor, when you multiply you are still getting 0. And then for all your point here, the value that you multiply now, it becomes the scale factor, correct? So that's why if let's say this is 2, that's going to be like 4. So that's why you will get a graph that looks like this. Okay, so the idea is you can see that now the minimum point also being stretched, the intercept here also being stretched, and also if let's say this is the part where you get y equals to 1. So now when it's being stretched, that meaning that maybe you will get y equals to 2. Okay, so that's the idea for stretching. Alright, so this is an example for 2fx as well. Okay, so now we are looking at the second part, which we talk about the vertical stretch. So this is y equal to f a x. Okay, so for this one, it's going to be a stretch with scale factor. Okay, and you must remember this is 1 over a. Okay, so don't be confused with just now the one. So this is parallel to x-axis. Okay, so let us try to use the exactly same example to illustrate. So meaning that, for example, if let's say this is my original graph. Okay, so it's the same thing like the picture above. Sorry, I can. All right, so this is at 2 as well. So can you try to imagine if let's say I have f 2x, how is that going to look like? So if I have f2x, meaning that it's a stretch with scale factor 1 over 2, correct? So meaning that now your function should be become smaller. So that's why when you try to stretch left and right, right? So what doesn't change is the point for x. Because when you multiply with x, if your x is 0, meaning that when you multiply, then you still get a 0. So that's why for this term, your y-intercept will not be changed. But of course, this and this is going to be changed because you are stretching it like to the left and to the right. So that's why if let's say it's 1 over 2, mean that you will get something like this. Okay, so for example, if let's say this point is like -2 and 2, now it will become like 1 and -1. Okay, so the inside one is actually for, sorry, I don't have enough space to, yeah, the smaller one is actually like f2x. Okay, so now if let's say what happened if I have another one which is f1 over 2x, then now your scale factor will become 2 because 1 over 1 over 2 you get 2, right? So now you will be stretching to your left and right. So for like double, so it will become like this. Okay, so instead of like -2 and 2, then it will become 4 and 2. Okay, so the bigger one, I should have write down bigger and smaller, but it's okay. Yeah, you understand lah? So the outside that one is for 1 over 2x. Okay, so same thing. Let's try to use this example again. So this is the graph that you have. Alright, so can you imagine if let's say you are stretching it, like if we are trying to draw maybe f1 over 2x, okay, so in a scale factor of 2 as well, how is that going to look like? So everything will getting stretched, right? So what doesn't change is your y intercept, because when you are stretching left and right, this is just like the middle point, so it's not being stretches. So for this part and this part is going to be like double up. Okay, and how about this part? Yeah, same thing, it will getting further as well. Sorry, it will getting further as well, but the y doesn't change because you are stretching left and right only. Okay, so meaning now this point must maybe move towards here. So that's why the graph that you will be having, it will be look something like this. Oops, sorry. Let me try to redraw. Okay, so it will still pass through the same axis. Sorry. Yeah, it's a bit difficult for me to, but you get the idea. So the minimum point is over here. Okay, so the same thing, it will move upwards again. So like this, and then go up. Okay, so this is the idea. So you can see like for all the y coordinate, it actually doesn't change. So what is being stretches is like from here to here. So if let's say this is originally like 1, then now your minimum point, the x, we are talking about the x as the x coordinate, okay? So the x coordinate might become 2 now, okay? So that's the idea. All right. So now let's look at a quick idea for combination for our transformation. So something that might be helpful for you to remember this is that normally for horizontal transformation, right, the changes made will be on the f of x or like on the y. So meaning that you see, if you want to do transition, right, it's f of x plus a. Then reflection is negative f of x. Then for stretches, it's like a times f of x. Whereas the other hand, for horizontal one, right, the changes always be made on the x variable. So when you try to do translation, a horizontal one, then it will be like x plus a. Then reflection one, then it will be negative x. Then after that, for the stretching part, it's like ax also. Okay, so this is something that might be helpful for you to like memorize the transformation. Okay, so let's talk about the last part where we discuss about the combination of transformation. So if let's say in the function itself, it's not only like one transformation being used, then how are you going to identify the order? Okay, so combine transformation. Okay, so this one is very important because normally, I mean, the question won't come out in like a single, if it's a single transformation, then it will be like quite easy lah. Okay, but it's just that if let's say it's a combine, then you need to identify which one come first and which one come later. Okay, so when we talk about combined transformation, right, for the case, if you have a horizontal transformation plus a vertical, meaning for example is a stretch parallel to y-axis and then translation to the left hand side. So this is like one vertical and one horizontal, right? So for this case, right, the order doesn't matter. Okay, so meaning no matter which one come first, you will still get the exact same function after you actually put them together. So that's why when you have one horizontal and one vertical, you don't need to really care about the order. Okay, but the problems come if you have the same type under the same category. Okay, so we start with the easier one first, which is like for vertical plus vertical. Okay, so for a vertical combined with a vertical one, so if let's say you have an idea of f of x become a fx plus b. Okay, so in this case, you will realize that there are two transformations that happen here, a stretch parallel to y-axis and a translation, meaning it's like moving upwards for b unit, correct? So in this case, what do you think that it happened first? Translation first or stretching first? So in this case, vertical plus vertical one, you always do it in like a normal algebra way. So meaning that when you look at this, then obviously that you will think that you will need to multiply a first, then after that you plus b, correct? So that's why this will be like from f of x. Then what happened is a stretch first. Okay, so stretch with factor a. Yeah, I'm just writing the shortcut, yeah. So factor a, then after that, this is parallel to y-axis. Okay, so now this become like your new function already, right? So what happened after that is that you have a translation. So for translation, it's going to be like fx plus b. So that's why this is your new function. So that's why I'm just going to plus b, which means this is how the order look like. So meaning that this is a translation for 0b. Okay, so which I think this part is quite easy. So you just follow the normal algebra way. So now we try to look at how about horizontal plus horizontal. Okay, so if let's say we try to discuss about maybe f of x, we try to change it to like f cx plus d. Okay, so no question comes. So same thing is a stretch, is a horizontal stretch and a horizontal translation. So do you think that translation happened first or stretch happened first? So for horizontal and horizontal, right? You see, if let's say we try to follow the same order just now, from f of x, if I try to do stretching, then what happened? So now it will become f cx, correct? Then after that, when I try to do translation, so the idea for translation is like f then x plus a, correct? So meaning now if I want to move d, then meaning that my x needs to plus d. So what happened? It will become f c x need to change to x plus d. So now what do you realize? You're actually getting cx plus cd. Is it what you want? No. You only want the stretches to happen before, then after that you only do translation, right? If we try to do this, then meaning that actually what happened here is like you do translation first, then you have your new x already, then after that you do your stretch, which is like not correct in this case, which we get cx plus cd here. So that's why the correct way in this case, it will be from f of x, you will need to do translation first. So meaning this is a translation to left hand side, which is negative d and 0. Okay, so you see when stretches happen, right, what happened to stretch is that you need to put f(a)x, correct? So that's why when you try to substitute, then you will try to substitute the x with ax. So now in this case, it's a scale factor of 1 over c. So that's why cx plus d. Okay, so this is a stretch for factor 1 over c and parallel to y-axis. Okay, so sorry, parallel to x-axis. All right, so this is something that you might need to be very careful when you try to solve for questions that involving combined transformation. Okay, so for vertical and vertical, you just do it like how you do it following the order for like how you solve algebra. But for this one, I mean, it's still a very logical, I mean, you can try to think of it like very logical, but it's just that you need to be mindful that you cannot multiply c then after that plus d, because the idea is we substitute the x. So that's why when we try to do translation, first we substitute the x with x plus d. Then after that, when you want to do the stretches, you substitute the x with cx. So if you try to turn it around, then later your c will need to multiply with c plus x plus d already, which is what happened when I try to show you the wrong example. Okay, so I hope that you can understand this part, and remember to always try out your latest past year paper for the transformation questions, because you don't have this content in your past year paper before 2020. Okay, so yeah, that's it for chapter 2. So thank you.